Okay, good morning, everyone. Welcome back to our today's class. Okay, let's go. All right. So today we're going to be looking at load analysis. Load analysis, as you can see it here, we want to design a slab completely. To show you how to design a slab completely, I think the load analysis I did before now is on BS code. That is BS 8110 part 1 1997. But what I'm going to be doing today, I'm going to be designing to Eurocode 2. Eurocode 2, that's what we're going to be doing. Eurocode 2. So I'll start with load analysis. Load analysis, and I'm going to start with the permanent loads. We have permanent load, we have variable loads. So for now, let's say you want to estimate the total weight of the slab. What you do is basically you go ahead and choose a particular height for your slab. Let's say, for instance, you have 150 mm, which is the lowest, then you have 175, you have 200, then you have 225, as the case may be. So you get, so but the one we are doing now, we are choosing 175 millimeters. You get, so when you convert the 175 now, you have 0.175. Then also this 25 here is called unit weight of the concrete. Unit weight of the concrete, which is in Eurocode 2, we usually use 25 kilonewton a meter cube. But if it was to be BS code, we'll make use of 24. Means if you are designing to BS code now, I mean this 25 now will now be what, 24. So we are here, we'll come over here and say self weight of slab. Self weight of slab is just like your overall thickness in meters, then multiply by the unit weight of a concrete, which is 25. And when you do that, you have 4.735. That means this is stress. This is a stress. Okay, this is a stress. Remember, because of the unit kilonewton per meter square, this is a stress. Let's go. Then the second one, we'll go ahead and say weight of finishes. Weight of finishes is just like what are finishes now? Finish is just like your plastering. When you're plastering, you understand the weight of that plaster is on it. Then let's say there's a tiles. You have a tile on your slab. Any other thing that can come on your slab, you understand? Those are finishes. That finishes. Then let's say down, you can't really estimate it. Let's just say we have it to be 1.2 kilonewton per meter square. 1.2 kilonewton per meter square. Then the next one will be partition allowance. Partition allowance is just like, let's say there are some blocks or some material that directly they don't come on top of a beam, they rest directly on the slab. So you get, so let's say you have an open space now and you want to use that place for a room, a sitting room, a kitchen, toilet, and so on. What will you do? The only way you can do it is to partition those area with either with any material. It can be block, it can be plank, it can be wood, it can be board, it can be anything, any material you can think of that comes under partition allowance. Let's say you can see the word say. So we are not really sure of that. We'll just say assume 1.5. Then the next thing you will do, you see your total dead load. Total dead load, which is your GK. Is your GK. So when you sum up this whole load here, it becomes there are load that they don't, once you do them, once you cast, they just remain. You understand? They just remain. They don't add. They don't subtract. We call them what? Total dead load. That is why we call it permanent loads. So total dead load now, our dead load in either BS code or Eurocode is still the same thing as GK. So when you sum this 4.375 plus 1.2 plus 1.5, you have 7.075 kilonewton per meter square. I think that is good enough. Okay, let's go to variable loads. Now variable load on slab, variable loads on slab, variable action, that is variable action or imposed load. We can also call this a life load. Life load, a variable action, and imposed load. Those are loads that it varies. Can't really determine what will be the total number of this load. Most times this load now can be how will I put it now? Let's say human, let's say you have a classroom, and the total number of people that are permitted to come to that classroom just like 20 or 40 for instance. Okay, let's say 40 for instance, and at the end of the day we keep having more than 40 numbers of students coming to that class. You get? So at times you might still not have up to that same 40. You can see most times the load will be very high, sometimes the load will be very, very low. You understand? So that one is a very good example of a life load or a variable action. And the second one is maybe you can have our furniture, your chairs, your stuff, your other things you have in your houses. You can decide one day you just want to take all those things off, bring in a new one. You understand? The old one and the new one you are bringing now, they don't have the same weight. You understand? So those are also very good example of a variable load, which can also be called a life load. So how do you know the number to use, the value to use, which is called QK? Most times to know the value to use, it also depends on how will I put it now? It also depends on the use of the structure. For instance, let's say for a residential building now, your hostels, your normal houses where you stay, you get, so can actually make use of 1.5 kilonewton per meter square. Do your research, browse what are the various life load values for different purposes of a building. You will see different values. So let's say residential, you can make use of 1.5. So if I'm already talking about commercial building now, you should know that the value will no longer be the same thing with that of residential. And we have different types of commercial building also. Some can be office for general use. Some can be just be some can just be um, hospital, different things like that. So the one I'm using here is because the use of this building is um, general office for general use. That's why I'm using 2.5 kilonewton per meter square. So that's for that. Then the what we call limit state ultimate limit state combination. Now I want to get the ultimate load that will come on the slab as a result of the dead load and the life load or the variable action or the core imposed load. Okay, I think here over here most times we are okay. Let's just say here now we have the ultimate load to be this YGK is this is I would should I call it Y, no, not Y, but this is just a factor. GK is just a factor. That has this GK shows is a factor for dead load, and GK normally is this GK that we have over here for dead load plus IQK or gamma QK, get, then multiply by uh, sorry, this should be QK, not GK. This should be QK. This here should be QK. Should be QK. Excuse me. Okay, please take this to be QK. QK, not GK. This should be QK. Now we are supposed to have maybe plus another factor and whatever the load will be. Let's say, for instance, in an area where you have um, a wind, when you have wind load, when you have snow, when you have earthquake, you consider those different types of load here. But here in Nigeria, where we don't really have much load when it comes to those things, so we only have our dead load and our life load, and then we move on. Okay, so this is exactly what I'm saying. Total load on slab, ultimate limit state, which is 1.35 GK plus 1.5 QK. This gamma GK now is what you have here to be 1.35, okay, plus this gamma QK now is what you have here to be 1.5. Get? So this QK, then the value for your GK and your QK, bring it here, bring them to this place. You have your ultimate load, which is value of n, now, okay. So when you do that, you have 13.30 kilonewton per meter square. Okay, actually all we need is not stress, because if you look at this unit now, we have kilonewton per meter square. We don't need stress. What we need here is a load, that is kilonewton per meter, is what we need over here. So what you're going to do is that, when, if you are very conversant with casting of cubes in the lab, if you did your project in the lab, or you have an idea, or you practice, you understand, and you actually want to test for the compressive strength of a material. Let's say you have the what you just do, you just take some little portion of the material from the granite, the sand, and other material you can think of, take them to the lab and use a mold. You get, use a mold, maybe mold of like 100 mm by 100 mm by 100. You understand? You get that? That means the once you now come up with a value which will now be the compressive strength, and that compressive strength now will determine the strength of the whole material you have on your site. The same way it is, you cannot design the entire slab. You only design just a small portion of that slab, and in this case now we are designing just to 1 meter section of that slab. That means I'm cutting just 1 meter, just a meter of the whole slab to design. So when you do that, you see 13.30 kilonewton per meter. Now this per meter run shows I'm running per a meter section. You understand? So 13.030 kilonewton per meter run. All right, let's go. So the next one now, structural analysis and design of the slab. All right, if you're in my last class, you follow the other video, you see where I brought this guy out from. Okay, good. I think we have it here. Look at this. Look at this. Look at this. I think I'm not supposed to have this. Okay, let me also do something here. All right, let's go. So if you should add up this value now, 3375 plus 2750, you discover that you have 6225, 6225, 6225. Okay. Mm, 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 Okay, let's look at it. Let's say if we have a column here, 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 and here. You can see this slab now is a 6225. You understand? So the next thing, let me do the same thing for this. Do this. Go. Okay. Then we'll see it 4725. So I'm working on this slab now. Let me go back. So let's say you can see 6225, 4725. Do you know why I'm doing this? Because it's the largest slab there is. We call it slab, critical slab there. Call it critical slab. Okay, critical slab. As I'm designing for that critical slab, because when provision I have here, I can use it to provide for every other side there on the panel. Or okay, let's go. So the floor slab is spanning in two direction. Since the ratio k of the longer side, which is this 6225, which is our ly now, to the shorter side, this is shorter side 4725, and it's called lx, which is less than 2, then it's tend to be what? A two-way slab. Now if the ratio of ly over lx is greater than 2, then it tend to be what? To span in one way, as shows in one way slab. Alright, let's go. And no, 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 no. And L over lx. which is this. We have 1.32, approximately 1.2, 1.3. All right, the next thing is you go ahead to get your moment coefficient. This is a formula for the moment. We have to be m equal to alpha n, which you have gotten before, lx. Then this alpha now that you're seeing is a bending moment coefficient. Now let's see how we can actually get this bending moment coefficient. So bending moment coefficient for two adjacent edges discontinuous. Now I think I will quickly explain something here. Two adjacent edges discontinuous. Let me use this. Let me use this. Let's say this is the one I have already partitioned now. Okay, before I will come and use this one now to explain something now. But before I will do that, let me just show you what we have to do here. Okay, so please try your best to download this textbook to really help you see how to design concrete structures using Eurocode 2. Okay, so let's quickly locate where we have that table there that we can use to solve the bending moment coefficients. Follow me, follow me. And see what we're doing. Trust me, to design is very easy, okay? Okay, I think we have a slab. How to design concrete structures in Eurocode 2. Yeah, we have slabs. So let's go. We'll soon get there. Okay, I think I will just use this as a short video. Explain the process to design a slab. Alright, I think we are here now. This is it. Now you can see bending moment coefficient for two-way spanning rectangular slab supported by beams. Now this is it. We have interior panels. We have one short edge discontinuous. We have one long edge discontinuous. Then we have two adjacent edges discontinuous. Now these four categories. Now what do we understand by this? Now before we come back to what is under each of them, you can see for interior panels now, we have negative moments at continuous edge. We also have positive moments at midspan. Even for this one short edge, negative moment and positive moment, you can see all of them for each of the condition. Let's say this first condition, condition 2, condition 3, condition 4, they all have the same thing. So let's go and check what we have. Okay, let's go back to this. Okay, let me look at this panel here. Okay, this panel now is 3150 and 4725. Now 4725, right? Now you can see that between this beam, between this column here to this other one here now, if you should check, this is a beam, right? This is a beam, right? This is just like, this is one of the long side of this panel. Then this one is the second long side of this panel here. Now if you look at this one from here to this side here, there's another beam. From here now, this is a beam we are talking about here. Above it, there's a beam. Below it, below this place now, there's a beam, which is this. That shows that this beam now is continuous on the side, on both sides is continuous. Then let's go to the second one. The second one now, which is this one now, you understand? This beam now is also continuous on this side because there's a beam above it. There's another beam below it, right? So automatically the two long side of this panel now, you understand, becomes continuous because they are beam after and before them. You understand? Let's put that. Then let's go for the short side, which is 3150 according to the value, please. According to the value, we have 3150 now, which is this, and which is this other one here. You get. So looking at this one now, looking at this on both sides, your to your right, to your left, there's a beam, right? There's a beam. So that shows that this beam now, this beam, one of the short side of this panel now, is continuous because it has a beam after, it has a beam before. You get. So that is for, that means the one of the short side is also what? Continuous. Now let's go for this. This now, this other one here, the other short side now. On this side, to your right, there's a beam. Okay. I mean, to this right is continuous. But to your left, there's nothing there, which is this side, nothing is here. You understand? So because of that now, this beam, this panel now becomes one short edge. That means it's only one short edge that is discontinuous. Like discontinuous, that means it does not have continuation. This is the last beam here. Which part now is not discontinuous? It's the short side that is discontinuous. I hope you're fine with this. Let's say this is not the beam that is a critical slab. I have the largest or the longest side, let's say both Ly and Lx, the biggest slab on it. Let's say this is what we have. You understand? And this is what we want to design, for instance, now. You understand? Like I said, always design the critical slab. Let's say this gives the critical slab now. And the condition I will now use there for the bending moment coefficient now will now be one short edge discontinuous. Let's go and check that. One short edge discontinuous. Are you seeing it? I'm going to use this second condition to design that. Okay, let's go. I think I've explained that. Let's go again. I think this one too is okay. Let me quickly use this as an example also. You can see that this is a, let's take this panel now, for instance. This panel, this is an edge panel. Let's take this one now, for instance now. Let's say here is 4725, here is 3075. Now this is the longest side of this panel, and this is the longest side also. This is shortest, this is shorter side. This is also the shorter side of this panel here. Now let's go. Now let me take this panel now, this beam now, this other one here. You understand? You can see above and below this beam, above and below this beam now, there's continuation of beams. Like above this, where I have this, right? Below this, I have this. So this beam now is continuous. Exactly. Okay. Let's go for this. For this one now, this one below it has a beam, which is this, but above it there's no beam there. Because of that, this one becomes discontinuous because it's the last beam here, becomes what? Discontinuous. Then for this, let's go for this. Let's go to the shorter side now. For this beam now, so this is the shorter side now. Okay, so before and after this, there's a beam. That shows that this particular one is continuous, right? So let's go to this one. This one now, after this beam now, there's continuation. Okay, but before it, there's nothing. You understand? So because of that, this also becomes discontinuous. So in a panel where you have one side to be discontinuous, one long side to be discontinuous, and one short side to also be discontinuous, that becomes two adjacent edges discontinuous because one long side is discontinuous, one short side is discontinuous. Okay, let's now assume that this is a beam, this is a panel now that give the critical panel. You understand? And you want to design this particular one at the edge here. You understand? Automatically this becomes two adjacent edges discontinuous. Let's go. Let me come over here and make use of this fourth one. Make use of this fourth one. Hello? That's more. Bitcoin, Bitcoin, abi, Bitcoin. Uh, oh, ṣé à ń gẹ́ fídíò ráì? Ẹ̀ ń lose owó o. Ẹ̀ ń lose owó náà, ẹ̀ ń lose owó náà, ẹ̀ ń lose owó náà. Dó bá mọ̀ ṣe àtọ̀. Okay, so I'm gonna make use of this. All right. Okay, then let's go again. Let's say, okay, look at this. I think I still love this. Now, for this panel now is 4725 against 3075. So these are the shorter side, and you can tell that the two shorter side now they are continuous. Okay, they're continuous, and these are the longs, the two long side, 1 and 2. But for this one here is continuous, because above and below it there's a beam. Then this one is discontinuous. This one is discontinuous. Okay, discontinuous. So because it's the last beam here. So if I'm to design this one now, this will become one long edge discontinuous, because is the longest side is the one that is discontinuous here. The discontinuous here. Okay, so that's just for that. And if I'm to design this beam now, assuming it's a critical slab, what I will just do, just come here, and you see one long edge discontinuous. That means I'm going to make use of this to design. You can see it. All right, let's go. Then the other one, let's go for interior panel. And I can take any of this. Let's say this now it can be an interior panel, because the first side, this, they are all continuous. So this can be an interior panel. Let's assume this is the one that is giving us the critical slab now. You get, so this automatically becomes continuous interior panel. You understand? So let's go. Interior panel, this becomes interior panel. Okay, so the one we are designing for now is this. We are designing this. We are designing this. We are designing this. We are designing this. Automatically, we are designing it to adjacent edges discontinuous. You can see it here. Just designing this. All of this now. Is it to adjacent edges discontinuous? All right, let's go back. You can see I have it as case 4. I don't need to come here and start writing interior panel, one short edge discontinuous, one long edge discontinuous, two adjacent edges discontinuous. You count which case do you have. Let's say, for instance, we have this can be case 1 interior panel. This can be case 1, case 2, case 3, case 4. So since I'm designing for two adjacent edges discontinuous now, this should be case 4, and that is exactly why I have case 4 here. Case 4 at this point. Okay. So under my value for L over LX is 1.3. Under case 4. Now let's go. Let's look at what this value will give us. Now case 4, which is this. These are the various values for L over LX now. We have 1.0, 1.25, 1.5, 1.75, 1. Then 2.0. But you can see I don't really have 1.32 or 1.3 here. What I just have here is just, I mean, my value is between 1.25 and 1.5. Okay, so let's go. And this, please take note, this is short span coefficient. Okay, let's say for the short span coefficient now, I have negative moment at continuous edge, which is you can see the value between 0.066 and 0.078. You understand? That means the value will not be less than this, and it will not be higher than this value, because my value is just like 1.32, 1.3. So let's see what we have here. You understand? Normally, you can do your interpolation if you know how to do that. Okay, you can see here, but this is negative moment at continuous edge. I have 0.069, 0.069. Then this 0.069, you can see it here. Then for positive moment at midspan, this is 0.049 and 0.059. The value will still be between these two. It cannot be less than this, and it cannot be higher than this. Okay, so what I will just do interpolation and bring it to value. Let's see what we have there. You can see I have 0.051. 0.051 is what I have there. Okay, I think that is good enough. Let's go back. Then you can see this is where the short spans stop. You understand? Then every other thing here is your long span. So irrespective of the one you are using now, you get, you just come here, pick your long span. That means these two now stand for long span. Okay, here now I have it to be 0.034, 0.045. You understand? So let me see what I have there. I think I did not adjust this, but let's leave it like that. You understand? So that is that, just to pick your bending moment coefficient. So once you're done picking your bending moment coefficient, you start your design immediately. So you can see I'm starting with design of short span. Design of short span now. Under the short span, I have the mid span. Under the short span, I have the mid span now. Okay. And the mid span value now, what is the coefficient? This is it. I have 0.051. Okay. So this is the formula for your moments. So put in that 0.051 times 13.3 by what LX raised to power 2. Now where is your LX? You can see this is your LX, right? The lowest value, shorter side of the panel becomes your LX. So that's what we have here. And once you do that, once you calculate this, try it, you have 15.143 kilonewton meter. Remember, we are still doing it per meter run. Okay, all right, let's go. So the next thing I want to do, the next thing I would love to do is that I would love to calculate this, my value for K. This K does not really have a name, it's just a factor. You understand? So I would love to calculate this. This MED over FCK BD square. Now let's define them. FCK is the characteristic strength of your concrete. Characteristic strength of your concrete, that is what your FCK is. And most times for Eurocode we can have it as 25, you know. Then B is the breadth of the section. Remember, we are designing to 1 meter section of the panel, right? So of the slab, you can see this is 100 mm, sorry, 1000 mm. Okay, then this D, the D now is called effective depth. Effective depth of a section. That is your D. This one you have to estimate for this. So the value should be less than or equal to 0.167. Okay, so we'll come back to that. So let's say for us to calculate for that D now, D is equal to H minus this concrete cover. That means you will not want to expose your reinforcement after casting. Okay, you want to expose that after casting. So then this is the diameter of the bar that you are using, that you want to use rather. Let's say you want to make use of 12 mm for this design. For the construction, I want to make use of 12 mm bar. So the diameter now will be divided by 2. So assuming the diameter 12 mm bars will be employed for the construction. Okay. Now remember the overall height that you made use of in your former design. Sorry, in this design that we're doing now, to calculate your load, you remember, is this 0.175. It was 175 mm. That was the overall height of the slab. And yeah, we have 175 minus. Now the cover, the spacing I'm using, now I'm going to suspend my reinforcement. Okay, suspend my reinforcement. I think let's do something. Now let's type cover to reinforcement. Let me show you what we're seeing. Let me show you a picture. Let's go to images. Okay, good, perfect example. Let's take this picture as an example now. Good. Let's take this picture as an example. Let's say this is a reinforcement you have on site, okay? And you don't want to place this directly on top of the formwork. You know what the formwork is now. You want to place it directly on top of the formwork. So what will you do? You will look for small stone to suspend your reinforcement. Okay, to suspend your reinforcement, you can. This one now on site we call them biscuits, but this is actually the cover to reinforcement. That means from here, where the this first reinforcement under now, where it's sitting to where the stone is, we take it to be 25 mm, 25 millimeters. Okay, so that by the time you remove this formwork under now, you understand your reinforcement will not be showing. And that one also depends on the hours of fire resistance. So let's go. So that we have 25. Remember, we are using this bar now. This bar now we are using that this bar now we are using 12 mm, right? So you can see divided by 2, you have 6. That is 144 mm. B, like I said before, to 1 meter run. So we have it to be 1000 millimeter. So let's go. We are taking this to be 25, FCK to be 25. So if you do that, 15.143. Remember the moment that we got here is in kilonewton meter. Wherever that's we have here, they are all. This one is 25 newton per millimeter square. This is millimeter square. That is 1000 millimeters. Okay, sorry, this is 1000 millimeter. Okay, this effective depth now is 144 millimeters square. Okay, just a square, you understand. So everything we are doing is just like newton and millimeter. So it will be very nice for us to actually convert this moment. Since is the only one standing there, we'll just convert it to newton millimeter. And how we convert that? If you want to convert from kilonewton to newton now, you multiply by 1000, okay? Then you convert from meters to millimeter, you also multiply by another 1000. That gives birth, that will give birth to 15.143 times 10 raised to the power of 6 good divided by 25 FCK divided by 1000 dB divided by D 144 square. So you can see the value is 0.029. Now it's actually less than 1.67. Now this, if it's less than 1.67, says, look at this, it says K is less than 0.167. It is singly reinforced and no compression reinforcement is required. And for this, they will call singly reinforced and doubly reinforced. Singly reinforced is just like when you have your reinforcement where we have tension alone. Understand? So when it's doubly reinforced, it's true that you have reinforcements where you have your tension. You also have a reinforcement when you have your compression. So for now, it's less than 0.167, so it is singly reinforced and no compression reinforcement is required. Okay, let's go. So Z now, this Z is called lever arm. Lever arm, LEVERARM, lever arm. Okay, so the formula is this: D in bracket 0.5 plus square root of 0.25 minus K over 1.133. Okay, less than or equal to 0.95 D. So if you calculate this now, the value of your K that you have is this 0.029. When you put it there, you know what you get. All right, so you have 0.974 D. You can say it's far more than that. It's higher than that. Therefore our value becomes 0.95 D, right? So let's go for this. You go ahead and calculate for area of section. Area of section now, the formula is MED over 0.87 FYKZ. So this is a moment, once again, you convert to Newton millimeter. FYK, remember, FYK is it's called characteristic strength of steel. Like, what is the ultimate strength of the steel material that you are using? It's called characteristic strength of steel. Okay, that's for that. Then remember that your Z is 0.95 D. Well, it's 0.95 times 144. When you do that, this will become the area of the steel is in millimeter square. But remember, we are still running per meter. So if you are done with this, calculating this area of steel, the next thing you do, you go ahead and calculate for your minimum area of steel that is required. Minimum area of steel required. And how do you do that? This is the formula here. There's the formula 0.26 multiplied by FCTM over FYK times B times D. You can also come to this book that I asked you to download. Locate, go to this page. Go to minimum percentage of reinforcement required. Now, for you to get your FCTM now, like I said before, this is it. To calculate your minimum, 0.26 multiplied by FCTM over FYK. This FYK, you already know it will be 460, right? You know this B to be 1000. You know this D to be 144, the one you calculated for. So what is now the FCTM? Let's go. FCTM will be, depending on the value of FCK that you are using. Yeah, the minimum FCK you can use is 25. Okay, you can see I am using 25. So if I'm using 25, FCK automatically becomes 2.6. 2.6, right? 2.6. So then 2.6. Let's go. 2.6. I will also come here. You can see I have 2.6. But if you don't want to do that, like you just want to calculate, if you go to EC2 on table 3.1, EC2 on table 3.1, you can calculate this. This is 0.3, FCK is 25, then raised to the power of 2 over 3. You can see we have it to 2.56, approximately same 2.6. So I will advise you, do not stress yourself. Come to this stage. Yes, and you can go ahead and just pick the value from them. That's that. Okay, so I have the minimum area of section or area of steel now to be 208.76 millimeter square per meter. Okay, so what we're going to do now, if you check this, we have been told there that this should be the minimum area of steel. Okay, like zero, you can see this is, you can make use of this formula or still make use of this one here, 0.13%. Let's go and see how we did them. So I'll come here and say 0.13%, show that it's 0.0013. That's what 0.13% will give if you multiply by 100, okay? Or divide by 100. So BD is, are you seeing it here? BD. Now, what you do next, you can see that we now have three area of steel now. The first one, the one we calculated for 276.598. Then we have the minimum to be 208.76. Also, we have the second minimum to be 187.2. Now, this is what you do. The highest value between the three of them, let me say the area of steel you calculated for this 0.26 and this 0.13%. The highest value between the three becomes your area of steel required. Since AS minimum is 187.2 mm square, which is less than 208.76, the area of steel required is equal to, that means automatically this becomes the minimum, because between the two minimum now, this is the highest. Okay, so I'll now compare with this one also. So the highest value between this and this one that I calculated for becomes my required. So what you're just supposed to do is that you provide a section that is higher than what you have here, 276. So how do you do that? Still go back to the material I asked you to download. Where is it? Let's try and get that. Let's try and get that. So we can provide. Okay. Okay, just go to, so let's go ahead. So for you to choose a section for you that you provide now, go to table 14 of the material I asked you to download. Hmm? You see table 14 of it, sectional areas of groups of bars, millimeter square. Well, the different bar sizes 8, 10, 12, 16, 20, 25, 32, and 14. Have okay, table 15. Please go to table 15. Leave this one. This one is for beams and columns. Okay. This one is for slab, the slab, staircase, and probably foundation. So on table 15, you have different bar sizes. You have different spacing. Okay. 75, 100, 125, 150, 175, 200, 225, 250, 275, and 300. Okay, so let's say I'm using 12 bar now. Please just go straight to 12 bar that you assume in the beginning that you want to use for the construction. Okay, so let's say here I will just have I'll be looking for, the area of section I have is at 276. Okay, 276 or so. So you'll be looking for a value higher than 276, and where do you find that value? Find it on 300 spacing. Okay, that means let's go 300 spacing, 377. Let's say now that means I'm supposed to provide watch. I'm supposed to provide white 12 That means I'm using 12 bar at this now is supposed to be like 300 center to center bottom. Area of steel provide. This will now be 377 millimeter square meter, bro. Okay, well, looking at this, looking at this, if you look at this critically, you will discover that the spacing for 300 spacing for a slab is too large, so large that to the extent that even your if bricklayers on site and people that knows nothing about building would first be the one to be asking you, would be telling people around that this engineer doesn't really know what he's doing. You understand? So to avoid such mistakes, you just adjust your spacing. So I think the one I can use here to manage and use it should be, let me say 215. You understand? 250. But normally, if I'm to do this professionally, I think I will use 175 or 150 You understand? So if I'm using 250 now, that shows I will be having 452 as the area. Okay, 452 as the area. If you are using 175, that shows you'll be having 646. And if you are using 115, that shows you'll be having 754. Exactly. So let's go and check. So for now, I'm using 250 please because I'm not okay with the space that I have here. So because of that, I will adjust down to 250. And let's go. So let's say this is what I have here. So I will go ahead and say provide white 12 at 250 center to center bottom. Then this is a provision I have. I think I'm done for that short span and mid span. I'm still on that short span. Remember that because of this you do it 4 times. Go of what you have here. These are 4 different coefficients now, right? So just like the one I'm still on the short span now, okay? And I've done this mid span. So I'll go ahead and calculate for this. Let's go. So design of short span, continuous edge, the same thing, same process, same process, shit, same process, same process, You retrieve this and use the same process. Same process. You have gotten 374. You know, I'd not even bother to even start calculating for the minimum because the 374 is even far higher than the 276 we got before. So I'll just assume that it's far higher than the minimum. Go ahead and provide. You can also provide the same thing, okay? 452 is far higher than 7374. So I'm good. So let's go. Then of long span. Then of long span now. I'll start with the mid span 0.34. 0.34 do the same thing. Therefore, this I will subtract 12 from it. Now I subtracting the 12 because the effective depth starts from the middle of the middle of whatever you have. Or you get this minus b, okay? So okay, so don't do that. Then when you're done, the same long span continuous edge. Please, this here, don't go and use ly. The ls still remain the same. The ls remain the same. Yeah, ls remain the same. Then design of long span continuous edge. Same lx here. There's no ly does not come in anywhere. Okay, so this value of k is go ahead. You can provide them. So if I'm done with that, I'll go ahead and check for deflection. Check for deflection. So we check for deflection at the short span and mid span of slab. That means for you to check for your deflection, what controls your deflection is your short span. Under your short span, your mid span controls the deflection. Or you understand all these things better when we'll be doing detailing. When we'll be doing detailing, you will get to understand all these things very well. Get to understand them very well. Okay. All right. So let's go. I think at this point now, before you calculate for your deflection, let's quickly check out something here. Quickly check out some stuff here. All right, let's come to this same book I asked you to download. See basic span to effective depth ratio. Basic span, let me see your basic span now. Should be, let's say for a two-way spanning slab, the check should be carried out on the basis of the shorter span. Okay, just like I said, the graph assumes simply supported span condition. K should be 1.0, 1.5 for interior span condition, 1.3 for end span condition, and 0.4 for cantilever. So in this case now, we're using 1.3 for end span condition. Let me show you end span condition now. This is an end span condition. It's not interior, it's not cantilever. You get? So that's why I'm using this to be 1.3 for slab simply supported at one end and continuous at the other end. I'm using 1.3. Let's go. Also, let's for that compression reinforcements, this to be 0. Now this is a formula, right? Your L over D, which is a basic span to effective depth ratio now, is K, no deal of this old formula here. But this is when where P is less than P naught, okay? Also, you can also make use of this formula when P is greater than P naught. Now let's go ahead and see what this density, this sign represents, and what this other one to represent, okay, before we come back to this one here. All right, let's go. So first of all, you can see I have two formulas here. I have two formulas here. So let me see what's this P? You can see this one is what I have here, okay? This AS provide over BD. Now AS provide at where? At your short span, your mid span. The AS provider is 452. Then the B is 1000. Then the D is 144. When you do that, you discover that you have 0.003. Then for this, your peanut, right? Okay, just like so. We have this to be 10 raised to the power of 3 times square root of FCK. Now, what's the FCK is 25. So when you do that, 0.005, you can see that this value is actually less than this peanuts now. Okay, so let's go. That means we are making use of this formula here. I'm making use of the first formula to calculate our L over D. So let's do that. L over D is 1.3 blah blah blah. Put it inside, and you have 30.838. 30.838, okay? 30.838. Then for this L over D, you can also do this without stressing yourself. Let's go back to what we have here. We can actually make use of the graph. Let's make use of the graph here. First thing, AS required over BD. AS required over BD, that is 0.03. 0.003, right? Percent falls within here between this 0, right? This 0.4, which is between this place. And if you come here now, you see different value for this. We are seeing it as FCK. You're seeing it as this first one, this first graph, 20, 25. We are seeing it as something like yellow, I mean, as this second one. Then 28, you are seeing that the third one, right? 30. So depending on the FCK that you are using, for now we are using 25, which is the second one, okay? So I will trace, this is the span effective depth ratio value now. So let me say my value 0.003 is within this place. Now let me say somewhere here. Yes, so I will trace this out, trace it out until I come across until I come across this value. So I come across this value here. Let's say I have it to be this. You understand, or 30 something across this value. You can see I don't need to start using this whole formula to actually get my L over D. You can do the same. You understand? So let's go back. Please, you can use this graph to pick your value. You can see you have 30.838. It's very, very accurate. So let's go. If you have gotten your basic span over effective depth ratio, the next thing you will need to do, go ahead and calculate for your modification factor. Your modification factor must not be more than 2. It should be less than or equal to 2.0. So this will be 310 over the stress. Now this stress now is like 310 over 500 times FYK. Multiplied by AS required over AS provide. This 310, 460, which 460 is coming from the characteristic strength of your steel. Then your AS required is 276.598. AS provide is 452. So when you do that, you have 174.5626 Newton per millimeter square. Do you know why we have Newton per millimeter square? Because this is area. This area to cancel out. This is Newton per millimeter square. These are just numbers. Okay, so you have this. Then put it back to your multiplication factor value. What you have? You have it to be 1.776, which is less than 2. So it's okay. I'll pick this value now. So there's what we call limiting span. Limiting span is L over D times your modification factor. If you do that, so your limiting span is 54.776. Now, actual deflection, actual span over effective depth. Now, this is your LX. That is your that I said your LX and your effective depth ratio controls the deflection. So this LX from here, remember this, your LX, don't you, that is why we use LX all through our calculation. Okay, you can see your LX here. Even when we're calculating for long span, we're still using LX because it controls the deflection. Okay, so this is your LX 4725 over 144. Here now we have a 32.8125. Now for your deflection to be satisfied, don't mind what I wrote here. For deflection to be satisfied, uh, this value here needs to be greater than your limited span to be greater than your actual deflection for it to be satisfied. Please change this to greater than. It's not less than. It should be greater than. That should be a mistake. It should be greater than. Okay. So, I think by God's grace, we've come to an end of this class. If you have any question, please drop them at the comment section, and also try your best to subscribe to this channel if you have not done that. Like the video and comment and keep watching. Enjoy yourself till meet in my next class. Stay blessed. Thanks for watching.